Yes. Wonderful. Okay, so in the interest of time, we'll start. So other students will be joining soon as they might be transiting from one class to another. So guys, join me in welcoming Mr. Tushar Sekhar. He is a senior engineering director of R&D at Blue Yonder. He has experience of more than 20 years in ideating, collaborating, designing, and delivering the products and solutions in the field of supply chain, forex derivatives, and consulting. Interestingly, he is our own alum of 2001 batch. He graduated from Department of Industrial Engineering and Management. The same department, our department, Industrial and Systems Engineering. At that time, it used to be called as Industrial and Management in 2001. And after that, he has been involved in, forex derivatives consulting, and for last 10 years he is with IT Technologies, erstwhile JDA, and now Blue Yonder. So I welcome Mr. Sekhar, and we are looking forward for an enlightening speech. But before that, I just give you background of our students. They are budding engineers, second year. They have taken first course on operations research. Also, I have invited my other students who have taken OR earlier. So some background of OR, as well as you have said, you will also talk a little bit of ML practices. And I must mention, guys, my students, that Tushar sir holds a lot of patent in the area of OR and ML. So I'm sure you will be, a lot to learn from how the OR and ML which you are studying actually changing the world. So over to you, Tushar sir. Welcome you again. Tushar sir, you are on mute again. Sorry.
All right. Good morning, everyone, and good morning, students. It's always great to be coming back to Close to Academia, interacting with professors, you students, and it's always learning, which is bi-directional. I learn a lot from you as well. I'll start sharing my screen, and please let me know when you are able to see my screen, and you'll have to give me a moment. Okay, so for some reason, Professor Akhilesh, I'm not able to share my screen. Would you have to give me permissions? Now I'm able to.
Yeah.
All right. I hope you are able to see my screen now.
Not yet. I will let you know once it is up.
Hopefully now.
Not yet for some reason. Student, guys, can you see this the shared screen?
No, sir.
No, sir.
Okay.
Okay. We one last moment. Just one more thing.
Actual logistics challenge in the real world, right?
Lot. They cause a lot of productivity loss.
Yes.
And let me do this. Let me just share this the PPT across to you, Professor Akhilesh, and if you can please share your screen.
Maybe if you try sharing the whole screen, that might help. In the meanwhile, you can send me the PPT as well.
Okay. Let me just for once. Let me try and rejoin.
Okay. So guys, feel free to ask questions. Try to understand how things work in the real world. Don't feel shy or anything.
All right, am I audible?
Yes, you are.
Okay, and I hope that I'm able to share my screen also. Now you should be able to see.
Yes, it is coming up. Wonderful.
Okay. Okay, so I have just prepared some slides which we'll go through. We are late by around 10 minutes, so I'll try to just gather pace and cover as much ground as possible. I'm one of you. I passed out from your place way back in 2001. After that, did some jugglery here and there, and now here I am at Blue Yonder. Okay. What we'll be talking about mainly is we'll be talking about optimization, operations research in general, right? And mainly when we are students, we don't understand, and I have gone through that phase, very intense phase, is that we don't really understand why we are being taught what we are being taught. Okay, how is it going to be useful for me? How is it going to be useful for the world in general? Okay, so we'll see some examples of how some of the very simple optimization techniques they are used to derive great value. Yeah. And no discussion nowadays is complete without a discussion on the ML. So we will touch some points regarding ML also, and we'll see how ML can be used in the overall system of optimization. Okay. Please stop me if you have any question anywhere. Please feel free and feel welcome to interrupt. Okay, see, I have spent a lot of my time in supply chain planning domain, right? So, and some of the examples that I'll be taking that will also be from the supply chain domain itself. So it's imperative that we get familiar with what the fundamentals of what a supply chain basically is. All right. So, Professor Klish, I'm still audible, I hope. Okay, right.
Yes,
So,
you are.
So supply chain basically is nothing but it is a set of connected nodes, locations, right? And through which items, the material, information, and cash it flows. Okay, so in very simple term, you can think of a packet of chips getting into your hand while you are enjoying, and this basically starting from the farming, right? So potatoes being harvested all the way to being processed, packed, shipped, stored, discount given or whatsoever, marketing done, all of that ultimately being in your hands at some great steal of the deal. Okay, this is what is supply chain, and supply chain planning is when you maximize the value derived out of all the activities which is associated with a supply chain, right? That is mainly what is supply chain planning and optimization. So you will see that optimization is at the core of supply chain, and I don't have to belabor on what is the importance of supply chain, right? I mean, all of us passed through horrible COVID phases, and still we were able to have our lives running. Okay, mainly because of supply chain, how well the supply chains were managed, how well the stores were managed, how the transportation were managed, how the factories they reoriented themselves to the new reality of COVID, right? So all of that is supply chain. If there's no supply chain, if there's no optimized supply chain, then I think it is not an exaggeration to say that then there is no life. Okay. So what are the challenges? Okay, I mean it is extremely challenging to run a supply chain operation, right? To optimize all the activities in the supply chain. Okay, and I've just gathered some snippets. Don't look at the actual numbers, okay? But I just wanted to show that how uncertain things are when you are trying to uh, optimize something. Okay, in this case, when you're trying to optimize your supply chain activities. Okay, so I think the students, you understand that supply chain basically it requires you running many activities well, and those activities are mainly where to produce, what to produce, how to produce, where to store, what to store, how much to store, right? And the same thing for transportation, same thing for the retail, where to distribute, and also other things like how much discount to provide, how much promotion to run. All of these activities are part of the supply chain optimization process. So The vital things are, as I already said, running the factory, running the distribution network. Okay. You look at the freight cost in the global supply chain now, it is obviously global. The things, parts and processes, they are spread across the globe. Okay. So you have to get the items across the oceans. And if you look at the freight cost has gone through the roof in the past couple of years. Okay. Almost 6 times. The oil cost, and this snippet I took before the Ukraine war, Russia-Ukraine conflict started. Okay. And you already see how much volatile the oil costs were. Copper and any other base metal for that matter, right? So in general, you would see that there's an increasing trend, but even when the trend is not so increasing, there's a lot of volatility. You look at this, there's a whole lot of volatility. Okay. So then it means that you have to be very conscious of the decisions that you're taking. All right. You would say, fine, no problem. What I'll do rather is that I will source all the raw material that I need. I'll source, I'll transport everything whenever I have the lowest cost available to me. When the oil is hit, somehow you find out this is the lowest in the oil, and then that is when you get everything at your facility, right? But then you also have to store. Storing itself, it is full of its challenges. The warehousing cost, if you look across the globe, this is an index, right? So it shows that how much is the variation of the warehousing cost across different locations in the world. Okay, so then you have to decide where to place your warehouse. Okay, if you are renting the warehouse, then where to rent the warehouse, and that basically is a facility layout. I'm sorry, facility location problem that you guys would have gone through. And then you said, fine, I don't need to probably rent. I will just go ahead and build my own. That is not easy itself. Just some numbers here, right, which basically shows that, the lead times are very uncertain. Okay, the construction is very, very prolonged, and it's getting extremely costly, right, to even build a warehouse. So all of these are constraints, and on top of that, the customers, they are also getting much more demanding, Okay, one of the surveys very recently done, it showed that around almost half of the USA consumers, they were they are open to shifting to the product which is shifting to the product which is cheaper. Okay, so it means that whatever you do, you have to do that at an optimal cost, so that you are able to give this to the consumers at an attractive price. Okay, any questions so far? Okay, cool. So so then how do, if the life is so full of challenges and so much of sorrow in the world, then how do people do what they do, right? We are still getting our potato chips, we are still getting our Nike shoes. Okay, so the answer is that it is a supply chain planning, or running a corporate for that matter, right? Is basically, it is a bouquet of many processes. Each of the process needs to be optimized. For example, when the customer gets very demanding, right? If they are willing, if they are sensitive towards price, then what you do is that you can, instead of increasing the price, you can actually reduce the package size. If you reduce up to 30%, the consumer will not notice. Okay, where does this 30% come from? This is part, so this 30%, by the way, this comes from some research, all right, but then within this 30%, how much do we actually reduce? For example, Tillamook is an ice cream producer. They very recently, they changed the package size from 53 ounce to 48 ounce. Okay, then, so I mean, why 48? Why not 46? Why not 51? Okay, so this, behind each of these decisions taken, there is a whole of operation research. And I mean, the world is rife with such examples. I'll probably not have time to go through many of those, right? But just be conscious that a whole lot of complicated stuff and a whole lot of operation research techniques to drive those complicated stuff. Okay. This you would have already seen, that what is the ORMS process. Okay. But just a refresher, that ORMS process is basically taking a real world problem, which is a problem which is seen and described in a concrete world, and then making mathematical models out of that, making abstract model out of that on which the mathematical playbook can be applied. Okay, outputs can be found, outputs can be analyzed, compared, the best model and the best output can be selected, and then that is implemented for ultimately for the interpretations and for actions to be taken, right? This is ORMS. Okay, and we will see how this in essence, right, this being the core, how this is used really to drive some of the very complicated decision makings in the world. Okay. Any questions so far? All right. So as I said that I have spent a lot of time in supply chain, so I will talk a lot about supply chain. Okay, and in that, I hope that if you are in second year, then probably you would have already had at least one paper on linear programming. No? What are the topics in operation research that you guys are already familiar with?
Vehicle routing problem.
I'm sorry?
Vehicle routing problem.
Vehicle routing problem. Okay. What else? Queuing theory? Graphs? Not those? Okay. Okay. No problem. So I'll try not to get into too much of complicated details. Okay. Okay, so let me, I didn't have any primer slide on the linear programming because that is actually going to be the base of a lot of things that we are going to discuss. But it suffices to say that a linear problem is basically a set of equations, okay, which are called constraints, and then there's an objective, okay. And what you try to do is you try to maximize or minimize the objective while always constraining yourself to those set of equations or inequalities, right? So there's an objective, there are constraints. Okay, I'll give you an example of the objective and the constraint. For example, if you have to, there's a very famous one which is called a nutrition mix. Okay. So if you have to, or let me take an example which is there, closer to what we have here on the screen is, suppose you have an enterprise to run, you have a company to run. Have you guys heard of the beer game? Okay, so
not yet, because this is the first course on OR. So the LP, transportation and assignment, this is what we cover. But yeah, beer game is interesting. They will come to know in next semester.
Okay, so basically, I mean, and you can probably Google that as well. It's a very famous and popular one, which is what basically it requires you to do as students and academicians is that they give you a real world business problem. I mean, real world meaning a representation of a business problem. Okay, where you have to run a company, and you have to run a company profitably, right? Subject to many constraints. Okay, let's take an example of Mahindra and Mahindra. Okay. So they have to deliver you the Thars and the XCV 700s in time, right? When you want it, and to the extent that you can wait. Okay, and they have to do that in a way that Mahindra and Mahindra still makes profit. Okay, and they do that in a way so that the suppliers from which they source, okay, they are able to give them high enough price so that the suppliers make profit. And then the suppliers, they have to do the same. Okay, maybe they are sourcing metals from somewhere, so they have to run their own supply chain. Okay. So what the overall objective here is that maximize the profit. Okay, profit is revenue minus cost. What are the sources of revenue? Revenue comes from all the sales. So basically the Thars and the XUVs and the spare parts and the services sold. Those are whatever you sell, that comes as revenue. Okay, and then minus the cost. What are the sources of costs? Costs are when you manufacture something, there's cost. When you buy something, that is cost. All sorts of cost. Okay, so objective is maximize revenue minus cost, subject to constraints. The constraints are things like my maximum production at my Pune plant cannot be more than 1 million unit, hypothetically. Okay, or I cannot have more than 40 trucks moving in a day from one plant to another distribution center. Okay, or I have 10 different suppliers, but I have to ensure that between those two suppliers, okay, I maintain a proportion of supply in a certain range. Like you cannot go below 20%, you cannot go above 80%. So these are constraints. And what you do is that you form a set of objective, which is basically a linear expression, and a set of equations or inequalities which define these constraints. And then there are techniques which you will learn very soon. They will let you optimize that. What is the best value of the variables so that my objective is defined, is achieved, and none of the inequalities or equations, they are violated. Okay. So that is NLP, and it is one of the very first things that probably you will read. And when you read that, you will see, okay, fine, this sounds very mathematical. How is it even possible to use it in the real world? Okay. So, but the fact is that it is used, and I'll try to take you through how. Okay. So supply chain, hopefully I was able to explain what it basically means. Okay. And in the real world, all the data is there in the database. Okay, so the transaction data, how much order you have expected, how much of Thars, XUVs, etc. you are required to ship. Okay, all of that data, your trucks, their capacities, plants, their capacities, suppliers, all of that data goes in the database. From the database, then the data comes into what is called the business layer, where you are moving from concrete world to the abstract world. The first step is that you represent that real world data as a set of your as a set of your not hypothetical, your logical models. Okay, so you would say that, okay, there was a factory, I'll represent this factory as a node. Okay, there was a supplier, I'll represent that supplier as a node. Okay, so like that, and you build the relationship between them. So you connect a supplier, or on the plant, you say plant dot consumes from supplier. Okay, something like that. Then when you do that, right, this part, in our case, this is in C++, but it could be anything. Okay, so this is code now. And then from code, then you go to mathematics. Okay, mathematics is that then these business objects, they get converted into a mathematical model. In this case, as you can see all along, this is basically a representation of a graph. Okay, it is a set of connected nodes and edges. So then we actually convert them into nodes and edges. We convert them into graph, right? And then from graph, we convert this into a linear problem, or a set of linear problems, right? So the equations, the objectives, I was talking about this, right? So there is minimize the total cost as an example, subject to certain constraints, right? And then certain bounds. Like you can say that whatever at a factory, whatever is incoming, right, whatever is incoming and whatever is outgoing, they need to be the same, subject to certain constraints. There's a basic conservation of mass. Okay, that as an equation, right? So then you convert them into, in this case, a mathematical model, in this case, an LP, linear programming model. And it is not a simple linear programming model which will suffice, because the business is extremely complicated. Okay, their goals are extremely complicated, right? So then what you do is that you define multiple objectives. Okay, so what are some of the objectives? Actually, the objectives, they look something like this, right? The CEO of the company, of let's say Mr. Anand Mahindra, he will say that I will need to manage my product availability. Okay, meaning right now XUV 700, if you go and try to book it, you will probably get an 18-month period, okay, waiting period. That is not desired. So they want to maintain the product availability. They want to be agile and reliable. Okay, what happens if instead of XUV 700, there is a different variation of Thar which becomes available, and the demand for that goes up, or another competition comes up and XUV 700 demand goes down. Okay, so be agile, right? Then customer requirements, product complexity, process complexity. You'll be amazed to see how many components are required to produce one seemingly simple product. Okay, so all of that, these are the business objectives. These are how the world is run. These are how the business is run. Okay, and these seemingly very, very complex business goals. They are met by doing this simple, right? At the heart of it, it is simple. Okay, process of converting a real life, a real world problem to a mathematical problem. Okay. Okay so far?
Any question, boys?
No, sir.
Okay.
Yes. Someone was asking some question. Can you please repeat? Tushar sir, I guess you can continue.
Sure.
If there are questions, I will communicate you through
Done.
email.
So let's look at a real world problem, right? I mean, actually, I've been talking a lot, but what is the value? Okay. So let me take an example of a semiconductor customer. Actually, I can name that. It is Micron Semiconductor. Okay, one of the leading manufacturers and providers of chips. Okay, so see the semiconductors. They had a very challenging past around 4 to 5 years now. Okay, even now everybody was affected during the COVID time, but even before the COVID time, they were hard hit by a whole lot of global mechanics, right? Global dynamics. For example, there was a big tussle between China and the Western world regarding Huawei. Okay, and there was this politics of tariffs and dumping duties and a whole lot of other things going on. So that basically creates a lot of disruption. Okay, for Micron, Huawei was one of the major customers. They were barred from doing business with Huawei, so that's a big disruption. Okay, then obviously with the COVID-19, the roof came down, right? So the way it started, I mean, if you look at now, thankfully things are almost normal, but you would remember that there was a complete shutdown. Then you'd say, okay, everything is shut down, so fine, it is shut down. What can we do? Anyways, okay. But it didn't go to that stage in a day, right? When it started with having a few corners of the world shutting down or putting restrictions, right? So for Micron, some of the suppliers, okay, some of the factories, supply locations were shut down. So then what would they do? The suppliers, they have the demand to meet from Micron. Then they would try to make up for that lost production in some other facility. When they produce it in some other facility, then the headache for Micron is that, and they also have to do their bit, right? So the headache for Micron is that now their lead times are going to be more. Okay, their parts are going to come from a far off location. Okay, so this was when it started, right? So they tried to compensate, and then eventually things shut down. Okay, so when things shut down, unimaginable, but people coped with that with whatever it is, whatever loss is there, loss is there. But then things started, right? Then when things started to pick up, right, it went through a V-shaped recovery, very, very sharp. When the demand started increasing, it was beyond the handling capability of any entity. Okay, so then that is another challenge of how do you cope with such increased, very, very fast rising demand. So these are some of these. And how did they tackle this problem, right? They tackled this problem by implementing linear programming at scale. Okay, one of the very simplistic things in the world of operations research. Okay, so what they did is global entity, very, very complex supply chain, right? They have a wafer. So the semiconductor, it starts with basically something called a fab, where it is the wafers of semiconductors, I'm sorry, they are fabricated. Then it's basically a chapati of semiconductor roughly, right? And then from there etching happens. Each of the wafers, they could potentially result into probably 1 million of the microchips. Okay, And then for each of those microchips, there are thousands of components. Ultimately, the IC that comes into you or my hand, or the IC that comes into your or my device, right? It's very complicated. Okay. So they had different problems to solve. Okay. So they build 10 different systems of linear problems. Okay, we call them instances. In each of these instances, there were as many as 700 objectives. Okay, and it was so huge that the solve times, right, they were up to 10 hours. Actually, we were involved, we provided the solution to them. And when it started, the run times were somewhere around 50 hours. Okay, a lot of research, a lot of other things went into bringing it down to around 10 hours, right? But eventually 10 instances, fine, complicated, all right, but at the heart of it, it was a simple linear programming set of linear programmings that was working. Okay, and it worked for them really. Okay, so when they came back with the results, there were an increase of 4% increase in the demand satisfaction. 4% is a huge deal for a global entity. Okay. The delivery performance, it was improved by 2% as much as, which is they were able to meet the demand 2%. And these are very upstream in the supply chain, right? So they were able to provide the chips faster to, for example, Sony, to Bosch, right? Or to other, again, manufacturers, and then they have to plan. So there's a bullwhip effect. Any small increase or decrease in the performance at that level results in a huge increase or decrease, right, in the performance when it reaches to us. Probably 2% improvement there would result in something like 20% improvement in the delivery performance when it comes to us. Us meaning us as the customers. Okay. They reported around 50 millions of saving in the working capital. Okay, every year 50 million savings. Okay. Around $15 million savings in the manufacturing costs. Right. So this is the power of the things that you guys are reading and learning, or are going to read and learn very soon. Okay. And again, if you fancy driving an XCView 700 right now, good luck waiting 18 months. But yeah, if things improve and more entities adopt such optimized processes, okay, you'd probably get these much faster. Auto industry, by the way, is still reeling under the semiconductor chip shortage. It's not just Mahindra and Mahindra, across all the auto manufacturers. Okay, any questions? All right. So there are more things that I have, but I think I'll go through some of these faster. So just for you to understand is, as we already saw, that one linear programming is not sufficient. A simple linear program is not sufficient. Okay, to solve one problem, they had to build 700 linear problems. Okay, and then 700 into 10 parallel instances. Okay, that is just one part of the process. Okay, that is what is called the aggregate planning. Okay, but that in itself is not sufficient. It's a building block in the overall process. Okay, it's a building block it's one cog in the wheel of the overall orchestration of these optimization. Okay, for example, the demands, how much demand do you plan for? We said that cost minus revenue, right? So you will go in with some demand in mind, that 1 million units is what I need to produce. Is that going to be 1 million, 1.5 million, or what? Okay, so that is demand planning. Demand planning is basically that this is where you the price elasticity, etc., it comes into picture. Okay, and a lot of machine learning technique, by the way, is used here. A lot of machine learning here. In my experience and knowledge in the entire supply chain spectrum, this is the place where I've seen the maximum use of machine learning. Okay, in forecasting. Okay, then when you have and by the way, you'll be surprised to know that some of the classical algorithms, they still outperform extremely sophisticated machine learning techniques. Okay, something like Lewandowski, it performs brilliantly. as compared to anything that you can think of in machine learning. So that is demand planning. Then it goes through a series of planning, right? They plan at different levels. So somebody will say, okay, we need to produce so much in this month at this factory. Then that will go to weekly planning, where people will say that, okay, in this week I need to produce so much on the daily basis. Then that will lead to the purchase orders, which will go to the suppliers that give me so much material on this date. Production orders, which will go to the factory shop, which will say, okay, produce so much on these days. The factory manager itself, it will take those, and then it will again run very sophisticated techniques to do daily sequencing as to exactly which machine to run on what minute. Okay, at the minute level planning is done there, and then that is fed into whatever is the production system. Actual production takes place. Okay. So in all these parts, and by the way, there's also a thing that how much you need to produce and store where. Okay, that is what goes into inventory planning. Okay, so linear programming, a lot of that is being here. There's a mixed integer linear programming. A lot of that is being used here. Linear programming is being used. A whole lot of this here. A lot of meta heuristics are actually in usage. So MILP also, but a lot of meta heuristics like GA is used a lot in this. Okay. Inventory planning, there's a whole lot of statistics here, a whole lot of statistical techniques and convolutions which gets used here, right? Machine learning, all of that. It's a bouquet of all the mathematical OR techniques that you have at your disposal. Okay, have you guys had enough of OR? Okay, if you have had, then let's also jump into a little bit of machine learning, right? Of how that is used. Okay, and you see the ML experts and the optimization experts, the purists, they are always not at a very good terms. Okay, that is because the nature, the approach to solving the problem is diametrically opposite. Okay, the classical OR world is very methodical. You take a problem, you create equations out of that or whatsoever, you create a model, do all of that. It looks pretty complicated, right? And what does ML do? ML, in short, you get a lot of data, or whatever data, however much data you can get, and you can handle. Get the data, train it. Okay. If it doesn't work well, train even more. Add more features. Keep churning till the time you get your answers. Okay. A lot of what it actually does is hidden. Actually, very few of us actually have the patience, rather, right, to go into the nitty-gritties of what the ML is actually doing and how it is actually able to give us the answer that we are looking for, right? But to the untrained eyes, it is data in, answers out. All right. So again, because I said I'm from the supply chain side and we'll be talking a lot about OR. So then let's see how the ML and the ORMS techniques, okay, how they actually combine. Is there a scope where it can be applied itself? Okay. So in the entire enterprise application ecosystem, there are different parts, and we saw that there's database layer, there's input layer, and then there's a business object model or the business logic layer, and then there's a pure mathematical layer. Okay, and then there is the result of all of these mathematical stuff, these great techniques. They go into another database for reporting and analysis. Then the decision makers, they have to make decisions based on whatever is the raw data, right? So that there is the value chain of data is basically there is data, and then there is information, and then there's knowledge, and then there's insight, right? So the decision makers have to take decisions based on the insight. Okay, but what they have available is data in tables and columns and rows, right? So at the data layer, there is a whole lot of there is a whole lot of ML techniques which are very relevant, and they add a lot of value. We will see there. Okay. At the data analysis layer, where the users and decision makers, when they have to take decisions and make judgments, right, there's a whole lot of applicability of ML techniques. right? In the business in the business layer, and when we are actually formulating the problem, there also it is tough. It is actually tough to make apply machine learning techniques directly here, right? But there's still there's scope. But when it comes to the core mathematical algorithm, okay, the classical OR algorithms, then it becomes very, very difficult to make it work with machine learning techniques. Okay, there are examples, but it is tough, and we will see how some of these things, some of the things that we have tried, and we are not the only people who are doing this. Okay, so we said, at the data input layer, at the data layer, what are the usage of ML? So there's a whole lot of data cleansing which needs to happen. There's a whole lot of outlier detection that needs to happen, right? And it's, you see, when you formulate the mathematical models, okay. Now hyperparameter is that would probably be known to all of you what it means in the area of machine learning. And there are hyperparameters which is not inside the model, which is on top of the model. Okay. Similarly, there are so many parameters which goes for the for the OR techniques or algorithms as well, right? For example, in linear programming, you have to say when you have to have a value of epsilon, right? What is that number? How low is the number so that you will consider that at as 0? Is that 10 raised to the power minus 5, 10 raised to the power minus 2, what? Okay, that is a hyperparameter, okay, as an example of that. So those kind of tunings, they are there. A lot of machine learning can be applied. All right, planning parameters itself. For example, I gave the example of this supply chain where there's a lead time. Lead time is basically the time that it takes to carry out any activity. How much time does it take to produce one batch of items? How much time does it take to transport a truck from my plant to a DC? Okay, these are lead times. And what is the value of lead time that you start with? Okay, typically somebody or some software or some person will actually put in that data into my database, and that is what gets picked up by the mathematical models, right? But actually that is not fixed. I just felt like putting whatever my machine is going to perform the same way as it had performed yesterday. If it took 1 hour to produce 1,000 items, that is what it will take today also, and that is what I'll just put into the planning for today. But not true. Okay? So then you apply ML techniques based on not only whatever is the intrinsic data, whatever data is available, okay, but whatever is the extraneous factors as well. What does the weather look like today? Okay, is there going to be, believe it or not, right, is ocean waves, the height of ocean waves, okay, that is tracked, and that is used to predict the transportation lead time of when will my container with 1,000 items actually reach my factory. Okay. So input detection, input prediction, a lot of ML techniques there. Okay. Yeah, so this at this layer. And I'll take an example. And Professor Akhilesh, please simplify this for the students. Okay, is so there is, you need to decide how much inventory, how much stock to store where, okay, and when. Okay, now again, auto industry, okay, they need to decide. Well, in auto industry, typically they basically source directly from the plant to the stores, and there's advanced booking, all right. But still they need to stock the different components, right, at factory. They need to stock, if something starts with plastic, right, and then that leads to probably 1,000 different plastic components in the in Mahindra Thar, okay, they can't wait for each order for Mahindra Thar to arrive, and then they will start, probably melting the plastic pallets. Okay, so they have to keep it ready as sub-assemblies, some semi-finished items. Okay. So then how much of those to stock, how many of those to keep? And it is at one point of time, it was assessed that around $3 trillion of inventory of stock, okay, useless stock is kept around the globe in supply chain because of inefficiencies. Think of that $3 trillion is a huge number. Okay, so that tells you what is the kind of impact that this inventory inventory decision, right, it has. So then what you need to decide is where to store, um, how much to order from the supplier. So assume of a sub-assembly, okay, let's say an LCD panel. You would say how many units to order, at what level do you need to order, right? Does my stock go below 100? Then I will order 200. Okay, so those kind of decisions, right? Now the thing is that think of all the components that are there in the supply chain for Mahindra Thar. Okay? You need to define for each one of those, you need to define what are your inventory planning parameters, what is the reorder point, right? What is the reorder quantity, okay? And this is based on manual rules most of the time, okay, or which is based on some rule of thumb that the planners would say, okay, you know what, if the customer is this, or if the demand is so much, then have 95% service level assigned to this. Okay, very stiff, and that has immense impact, right? You saw 2 trillion. Then what has been done is that a machine learning technique has been used, segmentation based, right? So basically it is KNN and decision tree, okay, which is used to look at the product attributes, each of the sub-assembly attributes, and a whole lot of other extrinsic features as well. And then that is used to create the segmentation, different segmentations, and then also assign for each of those segmenting a group of items. Okay, the inventory parameters that, you know, for these set of inventory, for these set of items or sub-assemblies, you know, I need to have not more than 95, I need to have not less than 95% probability of meeting the demand. Okay, and hence I need to have a certain reorder quantity and a certain reorder point. Okay. So this is an example of how machine learning has been used at the data layer, and then how it has enhanced the usage of classical optimization technique. Okay. Any question?
Tushar sir,
Yes.
we have 10 minutes left. I can see you are entering into professor's gear and started enjoying the teaching part. So, but we just have 10 minutes because the boys have class from 11.
Yep.
If you have time, I would like to invite you again, but for today's session, maybe we can conclude it in next 10 minutes. Thank you so much.
Yes. I'm reaching probably the last couple of slides, so I think we should be in time.
Okay, great.
Okay, so this is for those of you who think that OR क्या कर रहा हूँ, मुझे ML करना चाहिए, मैं ML ही करूँगा. You know, think of what ML can do when you combine that with classical optimization. And by the way, it is the optimization which is at the heart of ML. Okay, if you do not know what is a gradient, you cannot do gradient boosting. Okay, the whole lot of things. It is not just the core, but it is also how things are used. You know, people have used optimization techniques to find out how many number of GPUs to apply. You will train your models, but where will you train them on, right? There's a whole lot of, the GPUs have to come from somewhere. How many number of GPUs to assign to what problem, all of those. Anyways, as we'll be going off tangent here. Okay, so we said that at the input layer, data layer, a lot of things can be done. At the problem formulation level also, right? There's some other things can be done. It is limited, but still. And we'll see an example. Okay, so let me actually just jump into the example. All right. So sorry, my things are very LP heavy, but I'll still try to explain. So so we saw linear programming, right? So linear problem is basically an objective or a set of objectives, and then certain constraints, right? So minimize cost, subject to my whatever is the incoming equal to an outgoing, okay, at different places in my supply chain, and subject to certain capacities, like my total production on a machine on an hourly basis cannot exceed 5,000 units like this. So we have objective, constraints, and bounds. Okay. When you convert this into LP, then and when you actually solve it, right, you will see that it is actually gets converted into a matrix, right? So you have rows as constraints and you have columns as the variables. So for example, the production on a machine, if that is a variable, okay, and it appears in the constraint which says, you know, production of machine A plus production of machine B plus production of machine 3 is less than equal to 500, right? So then this variable appears in this row. Okay? So we have a row, a matrix formulation like that. Okay? And we would see that when we formulate this matrix, right, then it typically looks very sparse. Okay, if we have in this case, for example, close to 1500 constraints, right, and close to around 3000 variables. Okay, it's not very large. It's actually a toy data set. Okay, but we take that and we convert that into an image. Okay, and we visualize that as an image. You would see whatever white spots that you see here. It basically means that a certain constraints has some non-zero coefficient for a certain variable. Right? That is what it means. Okay? So when you solve this, okay, LP is a very notoriously hard problem to solve. It takes a lot of time, okay, and resource. So if you are able to take one large LP and able to, or let's just put it the other way around it. So if let's say you're taking 5 smaller linear problems and solve them individually, let's say it takes 2 minutes each. Total solve time is 10 minutes. But if you combine them together and solve the same problem, okay, even without making any change whatsoever, okay, then it will probably take, instead of 10, it will probably take 15 minutes to solve. You haven't changed anything at all. Still, just solve them together. That's about it. Yeah. On top of that, if these 5 different linear problems, if they're connected to each other in a way, then it will probably take, you know, much more, 30 minutes, even 1 hour, exponentially. If the size increases, runtime grows exponentially. Okay. So what we want to do is that as much as possible, we want to break down the problem into smaller chunks so that we can possibly solve them in parallel. Okay. And how do we do that? I mean, we try doing that by doing very many different things. Okay. But when you try to visualize it, we actually try to see what is really inhibiting that. We saw that there's some constraint, there are certain variables and constraints, right, which basically kind of bind together the entire part of the constraints. Let's look at this first. Okay, so in this case, you would see there is this part, okay, which is completely independent of this part. So no variable and constraint which are there in this part are also there in this part. So this entire matrix can be solved as 2 different matrices and probably solve them in parallel. And I just told you the benefits of solving in parallel or in breaking down. Okay. But that is it's the picture is not so rosy all the time. So when we actually formulate the LP, it is like this. And when you do this, you would see that it is very difficult to find you know, mutually independent parts of the matrix here, which is basically rectangular blocks which do not intersect. Okay. So in this case, what we did was we basically just applied some image recognition techniques. Okay. And then we were able to convert this you know, a monolithic matrix into smaller matrices which could be solved in parallel. Okay. And we saw that if we applied this technique, okay, then the size when we start, right, there is so 4500 constraints in the original matrix, and when it breaks down eventually, right, it breaks down into very tiny matrices. Okay, something like maybe 50, 100 rows at the max. Many of these can actually be solved even without applying any complicated solvers. They can be solved trivially. Okay. So what have we done here is that LP itself, this tiny little bit here, it is extremely difficult to maybe pass this to an ML technique, right, or apply an ML technique as to it. Some people are doing that, mixed integer linear programming. A lot of solvers actually apply ML techniques to find out the branching strategy and a whole lot of other stuff, but in general not. So what we have tried to do, we have taken the hard part, but we have applied ML on top of that, okay, so that an important business problem and mathematical problem, right, is solved. Okay. Yeah, I mean, I already talked about making insight out of data. So that's anyways, it's the run of the mill. The whole world is doing that actually. Okay, so that's it. I hope I'm not late. That's all that today.
Thank you very much. Guys, any questions? Very good question asked by Tushar sir, that ML karu ya OR karu, and you saw that OR problem, how with the MS processing he was able to use machine learning to solve an optimization problem, because in practice, as I said many a times, you have the example was anyway smaller than what I have talked about, where there can be 100,000 of constraints, and in the same manner the variables you have to deal with, and the challenge will be how to solve them in a, you have all the time in this world to solve the problem, but that will not help you in business. You have to be, solve it in a requisite time, then only you can help the businesses. So that's what he wanted to, highlight. Any questions? I know you have few minutes. If you have any questions, please feel free to ask. Do not worry about it is a silly question or what. Believe me, most of the, insights comes from the silly questions only.
Sir, presently there are three types of variables that are being used in LP. One is binary variable, another is continuous, and another is integer variables.
Okay.
So, sir, how can we sir, I have come across some problems where I think that some other variables might be necessary also. Like for example, if I want to extend the binary variable itself, like binary has 0 and 1 only, and I need suppose some other three variables arbitrary, suppose 5, 10, and 120. So I can also model this as a binary, like using binary variables. But in case I need, I want to reduce the constraints to a very low in number, then such variables are necessary which can directly take only these values. So it means what is the process of developing this? Because I have not come across any such solver which does something similar.
Actually, there are solvers also which do that for you. For example, if you are using Cplex, it gives a whole lot of high-level constructs where you can define. There are special order sets which will say only if this variable is positive, then other variables are positive. And then there are also piecewise linear constraints that you can define. So you can do that at a high level if you're talking about. At the low level, meaning when you actually have to write that in terms of equations, yes, you have to do that with the help of the integer variables and the binary variables. You combine them, you can do that. It's not very difficult to do.
Yeah, just to add on what Tushar has said, you need to define it as a set, that these are the values it can take, right? That's why he's saying that integer plus binary, you can define it. At Cplex, if you, I hope you have started working with Cplex. In that case, you can, at high construct, you can define all these numbers on.
Yes, sir.
Okay.
Sir, I have. Yes, sir. Sir, I have tried something similar. I found that, sir, for example, using the binary variables like, low-level binary variables.
Yes, let me interrupt you here. Okay.
Okay. Yes,
we can take it offline.
yes, sir.
Right.
Yes, sir.
Okay. Any other questions? My second year boys, the budding engineers, they prefer to be silent,
We all
we all were there. That's why I don't get very angry. That's why. Okay, guys, if you can turn on your camera and say, thank you to your alum, IIT Kharagpur alum, and that would be wonderful if you can turn on your camera for just a. Okay, they are sending hearts to the alum, but can turn on the camera and say thank you. That would be wonderful. Tushar sir, maybe you can stop sharing your screen so that
I'll stop sharing my screen. Yes.
Our voice can come.
Thank you, sir. Thank you, sir.
Right. Thank you. I All right. There's my window.
Okay, thank you very much, Tushar sir. On behalf of our class, our students, we are thanking you, and we are planning to bring you back again on the our meeting room. We would like to understand that image segmentation and everything. I hope it is not confidential. You can share us with that detail.
It's a product out there in the market.
Because so thank you very much, and we will be inviting you very soon. So you put on your professor's hat back, and we will be troubling you more. Thank you guys. Thank you
so
everyone
much.
for joining today. See you in class on Wednesday.
Thanks,
Bye-bye.
everyone.
Thank you, sir.
Thank you, Professor Akhilesh.
Thank you, sir. Bye-bye.